Good day, viewers. Welcome to our today's lecture. Today we are going to be looking at the above question, still under thermodynamic relations. We are asked to derive the following, which you can see on your screen, where A is equal to Helmholtz function by unit mass, of course, and G is equal to Gibbs function by unit mass. So, in order to solve this question, first we are going to let A to be equal to the function of volume and temperature. We are going to let A to be equal to this. Now we know for our fundamentals of partial derivative that this equation can be written as the A is equal to the partial derivative of A followed by the partial derivative of V, keeping T constant, the V, plus the brackets of the partial derivative of A followed by the partial derivative of T, keeping V constant, the T. Now this is what we have. Now we also know that Helmholtz function from our previous video, that is from our first video whereby we derive Maxwell relations, is nothing but the A is equals to minus P dV minus S dt. Now we can see that these two equations are equal. So we can equate the coefficient of delta T here and the coefficient of delta T here. If we do that, we are going to have the partial derivative of A followed by the partial derivative of T, keeping V constant, to be equal to minus S. So this is what we are going to have. Now we also know that Helmholtz function A is equal to U minus Ts. Helmholtz function A is equal to U minus Ts. It implies that I can make U the subject of this relation. It implies that I'm going to have minus U, which is equals to minus A minus Ts. If I multiply this equation through by minus, I'm going to have U to be equal to A plus Ts. Now this is what I have. Now from here you can see that minus S is equals to this. Minus S is equals to this. Now I can multiply this equation by minus S so that S will become the subject of this relation. If I do that, I'm going to have this equation to be the partial minus the partial derivative of A followed by the partial derivative of T, keeping V constant, to be equal to S. Now you can see that I've multiplied this equation by minus. Now I'm going to substitute the value of S, which is this, in this equation. If I do that, U will be equal to A. I'm going to substitute the value of S, which is this in this equation. I'm going to be having minus T into the partial derivative of A followed by the partial derivative of T, keeping V constant. So this is what I am going to have. So now from here you can see that I have successfully derived our first relation here, which says that U is equals to A minus T into the partial derivative of A followed by the partial derivative of T, keeping V constant. Now let's go for this second equation. Now Gibbs function G has been given to us. We are going to let Gibbs function G. We are going to let G to be equal to a function of pressure and temperature. We are going to let G to be equal to a function of pressure and temperature. Similarly to what we did here, we can rewrite this equation as the G is equal to the partial derivative of G followed by the partial derivative of P, keeping T constant, the P, plus the partial derivative of G all over the partial derivative of T, keeping P constant, the T. So this is what we have. So next, we know that Gibbs function, the G, from our first video where we derived our Maxwell relation, we know that Gibbs function, the G, is equal to V dP minus S dt. So what I'm going to be doing is that I'm going to be comparing this equation and equating the coefficient of delta T here with the coefficient of delta T here. If I do that, I'm going to have the G all over the T, keeping P constant, to be equal to minus s. This is what I'm going to be having. But for Gibbs function, h is equal to g plus ts. For Gibbs function, h is equal to g plus ts. G, of course, is equal to Gibbs function. If I make g the summation of the formula, I will still have my equation here. So what I'm going to be doing next is this. What I'm going to be doing is this. I have minus s to be equal to this. So I'm going to make s the summation of this equation here. It implies that this equation will be nothing but minus the partial derivative of g over the partial derivative of t, keeping p constant to be equal to s. Now I'm going to substitute the value of s, which is this, in the above equation. If I do that, h will be equal to g, h will be equal to g minus t into the partial derivative of g all over the partial derivative of t, keeping p constant. So from what we have here, you can see that I have just gotten our second equation which we are asked to derive, which is h is equal to g minus t into the bracket of the g all over the t, keeping p constant. So next, I'm going to be deriving our third equation, which says Cv is equal to minus t into the bracket of the partial derivative square of a all over the partial derivative of t square, keeping v constant. So next, I'm going to be deriving this third equation. How do I derive this third equation? We know that Cv, from our previous relation that we have been proving, we know that Cv is equal to t into the partial derivative of s all over the partial derivative of t, keeping v constant. We know that Cv is equal to this. So what I'm going to be doing is that previously I've just proven that the a from Helmholtz function all over the t is equal to minus s. Previously, I've just proven this. So what I'm going to be doing is that I'm going to be differentiating this equation with respect to t. I'm going to be differentiating this equation with respect to t. So I'm going to be differentiating this equation with respect to t. If I do that, I'm going to have the partial derivative all square of a all over the partial derivative of t square to be equal to minus the partial derivative of s all over the partial derivative of t. Keeping what? Keeping volume constant. Keeping volume constant. So this is what I'm going to be having. Keeping volume, what I have. From here, I'm going to be multiplying this equation by minus. If I multiply this equation by minus, I'm going to have minus the partial derivative square of a all over the partial derivative of t square, keeping v constant, to be equal to minus multiplied by minus is plus. Of course, we have the partial derivative of s all over the partial derivative of t, keeping v constant. Now from here, you can see that what is here is equal to what is here. It implies that I can substitute this in this equation. If I do that, I'm going to have Cv to be equal to minus t into the partial derivative square of a all over the partial derivative of t square, keeping v constant. Now from here, you can see that I've gotten my third equation. I have derived my third relation. So next, I'm going to be deriving this equation. I'm going to be deriving the fourth equation. This fourth equation. So to derive this fourth equation, we also know that Cp from our previous thermodynamic relation is equal to nothing but t into the partial derivative of s all over the partial derivative of t, keeping p constant. We know that this is correct. Now, from Gibbs function, which I've just derived lately, you can know that the g all over the t, keeping p constant, is nothing but minus s. From Gibbs function, this relation, I derived this relation previously. So next, what I'm going to be doing is I'm going to be differentiating this equation with respect to t, keeping p constant. If I differentiate this equation with respect to t, I differentiate with respect to t, I'm going to be having the partial derivative of all square of g all over the partial derivative of t squared to be equals to minus the partial derivative of s all over the partial derivative of t, keeping p constant, This is what I'm going to be having. Now, I can decide to multiply this equation, of course, by minus. I can decide to multiply this equation by minus. I'm going to have this equation to become the partial derivation all square of g all over the partial derivation of t all squared, keeping p constant, to be equal to the partial derivative. When minus multiply minus, we have plus the partial derivative of s all over the partial derivative of t, keeping p constant. So this is what I have. Now from here, what do you notice? You notice that this term here is equal to what is here. So it implies that I can substitute its value, which is this, in the above equation. If I do that, Cp will become nothing but minus t into the partial derivative square of g all over the partial derivative of t all square. So from here, it is visible, keeping p constant, don't forget. So from here, it is visible that I have derived the last equation, which is the last equation here. It says Cp is equal to minus t into the partial derivative square of g all over the partial derivative of t square, keeping p constant. So thank you for watching this video. I hope you find this helpful. Be sure to like and subscribe to our YouTube channel. The link to our WhatsApp group is also in the description below. You can tap to join and you will learn a lot. Thank you for watching.